My name is Jeremy, and today I'm going to talk to you a bit about the theory of plate tectonics. Most of what we know today about plate tectonics we've only discovered in the last 30 years. Before then, people assumed that the Earth was of one gigantic solid piece of mass, and that the way the Earth is shaped today was the same it was, for millions of years. Today we know different, but what are some of the evidences that we have that they didn't have? Well, basically, the most obvious one, which they also actually had, but was the matching of the continents, the outlines of these continents. For example, South America, how if you were to push it up against Africa, the west coast of Africa, it would fit perfectly. Not perfectly, but like close, fairly close. As well as India and Madagascar, if you were to take India off of Southeast Asia and link it up with Madagascar and the eastern coast of Africa, it also fits in really closely. Other evidence, not just to help with the plate tectonic theory, not just the outlinings of these continents, but the structures on them. For example, mountain ranges. More specifically, how the Appalachian Mountains matches perfectly with the Caledonian Mountains in Scandinavia and Scotland, Ireland, and Great Britain. They would match perfectly if you were to close out the Atlantic. Fossil matching is another great example of that gives evidence to the theory of plate tectonics. Geologists have found fossils in different areas all over the world that match with the same fossils. So how, unless they're the exact same species of what were existing in different parts of the globe, but these pieces of land must have been closer together in the past. For example, geologists found a fossil of a specific species of trilobite both in Newfoundland and in England that match. So it gives evidence to the fact that these two land masses were once, if not one piece, but at least closer together. Outside of these matching ideas, there is a slightly more complicated and scientific approach to proving plate tectonics, which is remnant magnetism of mafic igneous rocks. We all know that the Earth has a magnetic field, coming out of the north and south, meeting at the equator. They come out of the north and go down into the south, but at the equator it's the weakest part of the magnetic field, and closer to the poles it's stronger. These magnetic fields leave records in the rocks. Certain mafic rocks that contain magnetite basically take on the magnetic field of whatever is around it in the time of its formation, and then that's locked in history in that rock. So geophysicists and geologists are able to dig up these rocks and determine where the magnetic pole was at the time these rocks formed. Doing that, they were able to map out, the fact that it seemed like the magnetic pole was moving. If they were to take rocks from different areas of time, like different time ranges, the magnetic pole would be in different locations. Obviously, the magnetic pole is not actually moving. What's really moving are the plates, are the rocks themselves. So, it gives great evidence for the theory of plate tectonics. So let's go and describe a bit about what the theory of plate tectonics actually is. Basically, the theory of plate tectonics states that we are all sitting on plates that are moving. These plates are chunks of the lithosphere, and they're all floating, so to speak, on top of the asthenosphere, which is slightly less solid, more malleable. And we're moving on top of this asthenosphere. It's almost not exactly quite like chunks of wood floating on a ball of water, but obviously it's not that liquid, but it's similar to that. Because the lithosphere is it's a lot harder, it's cooler, so it's more brittle. It breaks up into these little chunks called plates. Now these plates are bouncing around, not literally, but they're moving, which leads me to the next topic of the boundaries, the plate boundaries. So when there's several plates, depending on who you talk to, there could be 8, there could be more than 12. But all these plates are bumping into each other. They sometimes slide under each other, they sometimes pull apart, and they sometimes slide by each other. So these plate boundaries there's three types. There's divergent, which is where they're pulling apart from each other. There is convergent or subduction zone, which when they are colliding, one's going under the other. And there's transform fault boundaries, which is when plates are sliding past each other. Examples of each. Divergent boundary would be the Mid-Atlantic Ridge, where the two plates are pulling apart from each other and new oceanic crust is being formed, roughly at the same rate of the average human fingernail. Then subduction zone / convergent boundaries, a perfect example is the Pacific plate coming up against the North American plate. The Pacific plate is going underneath the North American plate and creating a subduction zone. And what's important to note here is that it's always an piece of oceanic crust that is sliding under either another piece of oceanic crust or a continental crust. Another way to say it is continental crust would never slide underneath oceanic crust because oceanic crust is more dense or denser, so it'll always slide under continental crust. That said, that's what's happening at the west coast of North America. The North American plate is moving over the Pacific plate, creating volcanoes and earthquakes. Common volcano is Mount St. Helens. It's a volcano caused by this subduction zone. Also earthquakes that are very prevalent, throughout California and historic record. They're either caused by the San Andreas Fault or this subduction zone. The San Andreas Fault is an example of transform fault. It's when two plates are sliding past each other, and sometimes they get stuck, and they build up some potential energy, and then eventually they let go, causing an earthquake. San Andreas Fault is an example of that. Another great example is there's the tiny little ones in the Mid-Atlantic Ridge, and you can see it if you take a picture of the Mid-Atlantic Ridge. We can see how the ridge is coming down, and then it'll jut out and keep going. And that little slip there is a transform fault. So what's really important here is that those are plate boundaries, and another key concept with plate tectonics is continental margins, which can be confusing to some. It confused me at first. I didn't know what the difference was between plate boundaries and continental margins, but basically continental margins is wherever continental crust turns into oceanic crust. Now, they can either be passive or active, which a passive continental crust is any area where continental crust turns into oceanic crust without being caused by a plate boundary. A good example is Nova Scotia, where Nova Scotia's continental crust goes into oceanic crust, and there's no plate boundary for thousands of kilometers. I mean, the closest one is the Mid-Atlantic Ridge or the Pacific coast. An active continental margin is a continental margin that is a result of a plate boundary. So continental crust turning into oceanic crust because of a plate boundary. Now, the Pacific coast is a perfect example of that. And again, active continental margins is commonly where earthquakes take place, and volcanoes, well, volcanoes if it's a subduction zone. And that is my presentation. Thank you.